Hello, my name's Alan Foom, and this is the third part of my video on Fairway Evaluation. Here we're looking at yet to find estimation. So yet to find, or YTF, is a risk estimate or range of estimates of future undiscovered resource potential of a basin of play. So basically, how much are we going to find if we carry on exploring in the future? Now obviously this is highly uncertain and there are various ways of doing it, and I'll talk about all of them, all the ones I know of anyway. So why estimate yet to find? Well, all companies can focus their exploration efforts or new ventures efforts if you're going to buy into a new basin or new area, on areas that are more likely to yield results. Obviously there's no guarantee in this, but you're trying to scale the odds in your favor. See if a basin has future potential, or is it creamed out? Now I've talked about creaming curves in the last video, but this is looking at things in a slightly more statistical way. It's also used to some extent for promotion by governments and investors. Now, government geological surveys or energy departments or petroleum ministries publish yet to find estimates. I would take those with a little bit of a pinch of salt. The reason for that being that they have an interest in talking things up. And also on a more strategic level, looking at future energy policy. Peak oil supply, it's something that's gone a little bit out of favor, but oil is a finite resource, so you need to think how much have you got. And various bodies publish future estimates of what may be found. Obviously these are highly uncertain, but we need to have something which we can hang our hats on and we can talk about. So a little bit about stages within a basin. So initially you have frontier basins. These have a little bit of initial drilling, limited data, limited understanding. There haven't been any commercial discoveries yet. Now still there are some of those still left around, people looking at them, but we don't know if they're going to work. So obviously the range of potential future volumes is huge because we just don't know. Then you have emerging basins. Now these are early life. You've had some initial large discoveries. People excited about those places. So for example, in the most recent time, Senegal, Mauritania, or East Africa, offshore Mozambique, Tanzania, or just recently offshore South Africa with the Leopard discovery. People are excited and people look at these things and think, oh, this place could be. A few years back, Santos Basin in Brazil. Even further back, North Sea, Alaska, etc. Maturing. So you're now in midlife. You've made quite a lot of significant discoveries, but the discoveries that are being made are diminishing sizes as smaller features get drilled. Some novel plays are tried. Some of those work out. Some of those don't. And then late life, small discoveries, infrastructure-led exploration, trying to keep the facilities going. The big players may retain the core areas, or they may sell up. The concept of heartlands that's used within Shell. And new players may, however, emerge in the latter part of a basin life and may rejuvenate it. New ideas, new people, new ways of thinking. So this is a little graph of estimating yet to find. So you have exploration maturity with an increase in understanding. Obviously, the more mature you are, the more understanding it is. So initially, source rock yield, aerial yield, feature counts, prospect lead inventory, creaming curves, field size distributions. I'll talk about all of these. So this gives you an idea of different things that are yet to find. And I'll talk a little bit about each one of these. So aerial yield, quick and easy to do with minimal geological input. Is it really an analog? Limited scope for sensitivities? Nah, don't like it. Source rock yield. This is looking at bottom up, and we'll talk a little bit about later. Can either be relatively easy, you can spreadsheet very complicated using a basin model with high geological input. Creaming curves, low geological input, quick and easy to do. Zip plots, I really don't like. I'll talk about why in a minute. Summing your prospect inventory, again, very important because of the high geological input, and then feature count. So we'll talk a little about all of these, starting initially with aerial yield. This is quite simple. So for example, Basin A covers an area of 50,000 square kilometers, yields 5 billion barrels of oil equivalent, 0.1 million barrels per square kilometer. Basin B is that much bigger, therefore Basin B may have a potential of 7.5 billion barrels. Can I see the flaws with that? Are the plays truly analogous? Is it a similar reservoir? Is it a similar source? The trapping styles are the same? We don't know. What's the scope for sensitivities? Okay, you can increase or decrease your aerial yield. Don't know. Can't really use it in a meaningful way apart from a basic sensor, so I really don't like it. Next one I do like. This is a bottom-up approach where you're measuring how much hydrocarbon has been generated. So you map your source rock, you build a basin model, you figure out how much has been produced, how much source material there is, and how much hydrocarbon is given off. In this particular case, 200 trillion cubic feet of gas has been generated, expelled, but only about 10% of it has been trapped. Then your recovery factor gives you about 8 TCF recoverable resources discovered to date, 6 TCF potential yet to find using this. Obviously, the total hydrocarbon generators estimate has come with a great deal of uncertainty, as all basin models do. However, using sensitivities, you can figure out what may or may not happen. And you can do these basin models in software such as Trinity or Petromod, two excellent products that I've known seen used. Now, the drawbacks are still there. Your migration losses are hardest to calibrate. Now, as hydrocarbons are given off, they'll migrate to the surface because they're buoyant, but some of that will be lost and some of that could be trapped. Now, the trapped amount can be anywhere from 2 to 20% on average. That's a pretty damn wide range. And also, you have a situation where you allocate the volumes to different plays. You may have one source rock within a petroleum system, but it may feed several plays. It may feed a Jurassic play, it may feed a Cretaceous play, it may feed a Paleocene play. Well, how much has gone into each play? Again, your basin model can give you a bit of a guess, but you really need a pretty thorough knowledge of where things are. Then you've got potential for multiple source rocks, potential for biogenic gas, and the recovery factors are variable, so you get more uncertainty. Now, building a basin model is an essential part of the Fairway workflow, but this can give you quite a lot of estimates, which are really quite wide, but can still give you quite a useful sense check against others. Next one is creaming curve extrapolation. So creaming curve we discussed in the last video how that's made. So you got your well order, so numbers of well drilled versus your cumulative volume. So this is your history to date, and this is extrapolation from a historic trend. So that's your discovered volume, that's your yet to find. This is the asymptote where you think you're going to finish off. So that's your history, that's your forecast. Okay, useful visually, but does it really work? Not really. So this is an example from Central North Sea in the UKCS. So if you extrapolate from 1980, so this is what's been found to 1980. This is a rough picture. After about 100 wells, you think you're going to find 9 billion barrels. By 1990, you drilled a few more wells. You're kind of creaming out at 9.5 billion barrels after 500 wells. Then 2000, 400 wells have been drilled. You're kind of creaming out here, so that's looking a bit more positive as the high pressure, high temperature play came in. 2013, which is where you actually drilled 500 wells, you ended up with 12.5 billion barrels, significantly more than you thought you were going to have in 1980 because new plays were added. So this is the big drawback of a creaming curve, that changes in technology, changes in ideas, etc. can't really be incorporated very well. But it's a useful exercise to do in terms of giving you statistics on where you could be, and again, could be useful as a sense check. Zip plot. So this is for the missing fields. So effectively, you line up all your fields and you see what's missing. Now, I really don't like this method because there are a lot of difficulties with this, which I'll come to in a minute. And missing fields, again, you draw a green line within your field size distribution, and effectively these red arrows are the missing fields. Problem with this is, are the fields really missing? Does your basin really have this idealized distribution? Because most of them don't. If the field size distribution is irregular, it doesn't really work too good. Also, are your missing fields below your economic cutoff? These are very small fields which might never ever be developed. So this method can give you very misleading answers, and we heartily do not recommend it. Prospect inventory summation. So this method used by the British Oil and Gas Authority. Basically what you do is you have a prospect inventory, which is a list of all your prospects, mean, average recoverable volume, and a chance of success. Then you basically just add up all the means. You can put in cutoffs. So, for example, if prospects are too small to be economic, you can have a volume cutoff, you can have a risk cutoff. So anything with less than 10% chance of success just is never going to get drilled. So then you can come up with a yet to find from that. And this is what the British Oil and Gas Authority do, which is, I believe, a sensible thing to do. So again, it does have issues. It's dependent on the imagination of geologists, what the bias is. Is the entire basin and play being mapped? Now this is quite useful. Now OGA obviously have everybody's maps because every single operator in the North Sea produces the material to them. The volume estimates for prospect can be subjective, obviously imagination of geologists, as is the chance of success. Now volumes and chance of successes from farm outs tend to be, how shall I put it, optimistic. On the other hand, if a company is about to relinquish a piece of acreage, i.e. they want to demonstrate that it has limited prospectivity, so thank you very much, here's acreage back, Mr. Oil and Gas Authority, they would tend to produce slightly pessimistic estimates. The cutoffs can be subjective, and sometimes you can have the same feature interpreted by different companies with quite different results. But it's a useful idea of where prospectivity currently is. Another way of doing it is modeling stochastic feature counts. So this is where you're looking at statistics within a basin. So size range of the features, what recoverable volumes there might be within them, chance of success of the play, your fluid parameters, and a number of features to be drilled. And you put them in a stochastic simulator, something like the GeoX program, and out will come a set of stochastic results. Now, a former colleague of mine likened this to the Drake equation for search of extraterrestrial life, because you don't really know what the inputs are. On the other hand, you put in different variable inputs to come up with results of what could be plausible. Now, it could be used very effectively in basin screening, and the inputs can be varied to quantify the impact. Hardest parameter is the number of features, particularly in an area which hasn't been fully mapped. It usually can be quite a wide range. You can guess an untested play using analogues, again subject to a wide range. You can also use this method to work backwards. For example, if you're building a liquefied natural gas export plant and you require 12 TCF of gas to be discovered within a basin, to fit that, you can figure out what's the likelihood of doing it by running these stochastic models, and if the inputs look implausible, then your chances of building an LNG plant are relatively small. The United States Geological Survey, USGS, use this in the World Petroleum Assessment. So this is their flowchart, so selecting minimum field size, assigning geological risks, etc. And outcome, a set of probabilistic outcomes, P5, P50, P95. And this is what they look like. So you have a distribution curve like that. So the P50 is here, the mean is here. And they have very long tails. They have a log normal distribution. Now, they've also produced this for the UKCS, for the North Sea. And a paper by Stoker et al. Looked at the USGS estimates with their own way of doing it. And this is prospect mapping by DTI, the former predecessor to the OGA. And you can see that the low cases are actually very comparable, but the tail on the USGS is very high, so it pushes the mid-level up further than perhaps it needs to be. And there was quite a lot of discussion about this within the geological community, with obviously rebuttals by the USGS. So, to sum up, all YTF methods have estimation methods have benefits and drawbacks. It will be a good idea to use several methods to compare the results, knowing the drawbacks of each method. However, there's a challenge. The management tend to like a precise answer. Some of them just want one number. Smarter management kind of want a bit of a range, so they want three numbers, a low case, a mid case, and a high case. But you need to quantify, which is a very uncertain estimate. So perhaps looking at what's the likelihood to reach a threshold. The management demand a billion barrels of oil equivalent to be found. What's your chances of getting that? And you can use various methods to try to get that. So you also need to look at the motivations of people providing YTF estimates, particularly external people. Governments that are trying to promote hydrocarbon exploration, companies that are trying to promote the acreage. Your own estimates you should try to be as unbiased as you can. Obviously that is difficult because we're all human. New untested plays are hard to model, and the key point, again, past performance does not guarantee the future. Thank you very much.